Have you ever wondered what holds everything together? I mean, really, everything. Your desk, the air you're breathing, it's all built on a set of invisible rules. Tiny little atoms linking up in this precise, unseen architecture. Today, we're going to pull back the curtain and look at the fundamental forces that build our world. I mean, think about it. Why isn't everything just a chaotic soup of lonely atoms floating around? Except for a few standoffish types. Atoms just don't like to be alone. So what's going on? What's the invisible glue that pulls them together to create, well, all of reality? That's the mystery we're diving into. So here's our game plan. First, we'll look at the social life of atoms, why they even bother to connect. Then, we'll uncover our first big clue, this elegant rule of 8. After that, we'll see where that simple rule kind of breaks down, which leads us to the secret of 3D shapes. And finally, we'll get into how atoms really form those bonds. Okay, first up, the social life of atoms. You can kind of think of it like this. For most atoms, being alone is a really high-energy, high-stress situation. They're basically just buzzing with this nervous energy, always looking for a way to calm down, to find a more stable, low-energy state. It's all about finding that stability. And this isn't just some vague idea. It's a fundamental law of the universe. As one of our sources puts it so perfectly, every system tends to be more stable. This whole process of chemical bonding, it's just nature's way of chilling out, of lowering the overall energy to get to the most stable arrangement possible. So we know the goal is stability, but what does a stable atom actually look like? Well, the first big clue came from looking at the cool kids of the periodic table, the noble gases. These guys are perfectly happy being alone, totally unreactive, and scientists figured out their secret was hidden in their electrons. And that secret is what we now call the octet rule. It turns out that having 8 electrons in your outermost shell, well, that's like hitting the atomic jackpot. It is the ultimate configuration for stability. So, other atoms will do pretty much anything, gain, lose, or share electrons, just to get to that magic number 8. So, how do they get there? Well, there are 2 main strategies. First, you've got the ionic bond, which you can think of as the thief. This is where one atom just straight up gives an electron to another. This creates a positive ion and a negative ion, and you know what they say, opposites attract. Then you have the second strategy, the covalent bond, or the sharer. This is where 2 atoms decide to share a pair of electrons so they can both pretend they have a full, stable shell. And to actually visualize all this electron swapping and sharing, chemists came up with this brilliant little tool called the Lewis structure. It's basically a 2D blueprint for a molecule. You just count up the electrons, draw some lines to connect the atoms, and then sprinkle the rest around until everybody's happy with their 8 electrons. It's a really powerful way to sketch things out. But, and there's always a but, isn't there? This is where our neat and tidy 2D model starts to run into trouble. Because as we all know, the world we live in is not flat. And this is the problem stated perfectly by one of our sources. The whole octet rule and these Lewis structures, they're great for bookkeeping, for keeping track of the electrons. But they tell us absolutely nothing about the actual, real-world 3D shape of a molecule. And as we're about to see, shape is everything. Let's just take one of the most famous and important molecules of all time. Good old H2O, water. Now, if you draw the Lewis structure for water, this is what you get. Looks totally fine, right? A nice, neat, straight line. H-O-H. Based on this 2D model, you'd be totally justified in thinking a water molecule is flat and linear. But in the real world, if you could actually zoom in and see a water molecule, you'd see this. It's bent. It's not a straight line at all. And that little bend is the reason for almost everything special about water. It's why ice floats. It's why it can dissolve so many things. It's honestly a huge reason life on Earth is even possible. Our simple 2D model completely missed the most important part. So clearly we need a better theory. So what explains the bend? How do we predict these 3D shapes? Well, the answer comes from a theory with a really clunky name, but a beautifully simple idea at its heart. It's called VSEPR Theory. VSEPR stands for Valence Shell Electron Pair Repulsion. Yeah, it's a mouthful, but the core idea is so intuitive. All those electron pairs in an atom's outer shell, they're all negatively charged. And what do like charges do? They repel. They push each other as far apart as they can possibly get in 3-dimensional space. And that arrangement is what dictates the molecule's final shape. So, the basic rule is simple. Electron pairs push each other away. But here's the crucial detail, the secret ingredient. The lone pairs, those electrons that aren't tied up in a bond, they're extra pushy. They take up more room. You can think of them as having sharper elbows. They shove the other bonding pairs more aggressively. And that's the key detail our 2D model was missing. And with this one little tweak, VSEPR theory becomes this incredibly powerful predictive tool. Just look at this table. Let's go back to our water molecule. Look at that last row. The central oxygen has 4 pairs of electrons total, but 2 of them are those pushy lone pairs. So they squeeze the 2 bonding pairs closer together and boom, you get a bent molecule. It's not a straight line. The mystery is solved. Okay, so VSEPR theory is amazing. It predicts the shape, but it's still just a model. It doesn't really explain how the atoms are actually pulling off these geometric feats. For that, we have to go one level deeper into the wonderfully weird world of quantum mechanics. And let's be super clear, VSEPR is fantastic. Using these simple rules of repulsion, you can predict the shape of tons and tons of molecules with startling accuracy. It's a workhorse of chemistry for a reason. But if you want to understand the why, the physics behind the shape, you need something called Valence Bond Theory. This gives us the quantum mechanical reason for the shapes that VSEPR predicts so well. Take methane, for example, CH4. VSEPR tells us, correctly, that it has this perfect pyramid shape, a tetrahedron. But here's the problem. A normal carbon atom's orbitals don't look like that. They're not pointing in the right directions. So to make 4 identical bonds, the carbon atom has to do something incredible. It literally remodels its own electron orbital. This process is called hybridization. The atom basically takes its existing orbitals, which have slightly different shapes and energies, and it mushes them all together to create a brand new set of identical hybrid orbitals that are perfect for bonding. For methane, it blends 1 s orbital and 3 p orbitals to make 4 new sp3 orbitals, all pointing to the corners of a pyramid. It is the quantum how behind the VSEPR what. So let's just zoom out for a second. We went from a simple rule of 8 to the 3D reality of electrons pushing each other around, and finally all the way down to the quantum mixing of atomic orbitals. It's a journey that really uncovers the hidden architecture of reality itself, and it kind of leaves you with this one big question. If our entire physical world is built on these tiny, elegant, invisible rules, what other unseen systems are out there?